the original electrolytic, which was built inside of, or the electrolytic can, I should say, which was built inside the sweep generator, went bad, and somebody somewhere in the past built in two electrolytic capacitors on top of the bad one, but instead of cutting loose the bad one, they simply soldered the two replacement capacitors to the lugs of the existing can, which is not a very good idea, since if that original electrolytic would short, then you would be really in trouble with these ones tacked well, in parallel, in fact, to the original one. So that's really not a good idea. So I'm going to extract them, and then I'm going to see whether I'm going to stuff the old electrolytic can or not. I'm still of two minds. And this is what half an hour of cleaning with ammonia can do against 60 years of accumulation of grime. Can you tell the difference? I think you can. The part on the right was cleaned with ammonia. The part on the left and the bottom part weren't cleaned yet. And I think you can tell for yourselves there's quite a difference.
So I shouldn't be telling this, but that mug was given to you by your boss, and he's right in this room with us, and he's over there, and he's watching.
Okay, so let's get on with cleaning. I was right. The RCA jack, well, at least one of the RCA jacks that was on front of the cabinet was and you could say an aftermarket addition, or maybe an alteration some tech or maybe some hobbyist in long past times had made to it. Now I'm still trying to figuring out what those alterations do exactly, but in any case I think I will keep them, but I will alter the jacks for BNC connectors. And well, you know, these BNC connectors don't cost the end of the world, and should it not be useful, this alteration, I can still remove the BNC jacks and replace them by the original jacks, RCA jacks. Well, I should say false original RCA jacks. The engineers at RCA were so nice to mark or to stamp into the chassis the type numbers of the tubes. I don't know if I can show you with the camera, but I think you can just about see it over there. There you go. So you see, they stamped into the chassis the codes for the tubes. You have the 6C4 over there, right there, and then you have the 6AX6 over there, and then you have the 6X4 over here. So yeah, they were quite nice to do that, and it's an interesting little detail. Okay, I cleaned up the shield tubes a little bit. Well, it's not really necessary, but well, it's sort of a nice detail, let's say. Right, what else can I show you? Well, I changed this whole dirty resistor assembly, which was up here, and I replaced it by these two resistors. Both are 3 watt rated resistors, which makes it a little bit less cluttered, and it looks better anyway. Also, small detail, this resistor here, yeah, the original one, was supposed to be tacked to this lug here, and it wasn't. It was loose. It was hanging loose in the air. So my guess is the guy who soldered them in hadn't done a really very good job. Also, the two resistors which were above the one which was here were kind of tacked together in parallel to make the right value for down there, yeah, which is a 33 ohms resistor. I guess they ran out of 33 ohms and they sort of cobbled together a resistor by placing two resistors in parallel. Great. Okay, so what's next? Well, at the back, you remember, there was a very big resistor. It actually measured quite good value-wise, but I didn't like the look of it, so I replaced it. So it was this resistor here, which is supposed to be a 1.5 ohms 2 watt resistor. Now look at the difference. You see this one here, and then look at this one. What a difference, eh? And this is rated for 2 watts. This one is rated for 3 watts. That's a big difference, isn't it? Anyway, I didn't like the look of it, and so I replaced it. It seemed like the right thing to do, even though it measures okay. Yeah, well, you know, I really didn't like it. Anyway, off with it. Right, then the next thing to tell you is that this thing here, which I cleaned up, as you can tell, I cleaned it up, is really a variable capacitor, and actually I should say a dual variable capacitor. Let me show you on the schematic. Okay, so if you look at the schematic and you look more specifically at this part, then you'll see here where is marked attenuator, you see these two capacitors here. Well, that's exactly what that tube is over there. It's a variable capacitor. Why they had to build it in such a kooky way, I don't know. I suppose they did that just to make sure that there would be no high frequency signal leaking out of this central box. Yeah, so this whole assembly here is meant to keep RF, I mean swept RF, within the box, and that's it. And this coupling capacitor, which you see here, is built in such a way that when it leads out the signal through this black wire you see hanging from it, then the only possible RF leakage you would get is from this very thick coaxial cable here. Yeah, but since it is coaxial, it will probably leak very little RF signal to outside, And remember, the whole case, the whole box, or cabinet I should say, for this sweep generator is metal. So my guess is the engineers at RCA were very careful not to have any sort of RF frequency leak away from the box, radiate out to influence other equipment, which is a nice touch, I would say, but let's face it, it makes it a lot more complicated. Right, so what's next? Well, what is next is that I will first check the secondary of the power transformer. I know the primary is good, and I have an indication that the secondary is good. The secondary of the power transformer, and I mean the 300 volt secondary, comes in on pins 1 and 6 of the 6x4 rectifiers. Okay, so as you can tell, it's a winding, a secondary winding with a center tap going to ground. And what I want to do is to measure whether there's continuity here and get a reading for the resistance of the coil. Okay, so pins 1 and 6 of the rectifier tube. Alright, I wasn't getting any reading because the pins of my multimeter apparently were too large for the socket. Now, there is another way, of course, to measure the secondary of the transformer, which is to place one of the leads against the chassis, which is ground, and then measure both halves of the 300 volt secondary. So I'm going to do just that. I'm going to clip my lead to a crocodile lead and then connect it up to a nice ground point, which is here, there. Okay, and now we're going to measure from the tube pins, and I think you can just about see where I'm going to measure. Okay, let me show you from a better angle. There, I think you can just about see it. So first I'm going to measure the resistance for pin 6. Okay, so let's measure pin 6, which is this pin here. Oh, hang on. Okay, so there you go. That's about 256 ohms, okay? So one side of the secondary is 256 ohms. Okay, so that's measured from pin 6. Now let's go over to pin 1, which is there. Okay, hang on. Okay. And that measures 272 ohms, let's say. Okay, so we have 272 on one side and 256 on the other. So let me see. 200. Hang on. Yeah, 272. So 272 plus 56, 72 plus 56 is 120. 32 is 128 plus 400 is 528 ohms in total. Okay, let's see if we can measure that. Okay, here we go. Right, so now let's measure pin 1 again. Hang on. Yeah, well, okay, 527 ohms. So I would say the secondary 300 volts is okay, which is great. Yeah, and we're going to mark that down on the schematic. It could be useful for later reference. So 528 ohms. Right, now we want to measure the filament windings, and that is a little bit easier. One part of the filament winding of the secondary, let me show you, one part of the filament winding, which is here, yeah, which goes to ground, as you can tell right here. Okay, so we're going to measure at any one tube, and since we have the 6x4 readily available, we're going to measure at pin 4 of the 6x4 and see whether we can measure anything between ground and this pin of the winding. Okay, so saying pin 4 of the 6x4 and between ground, so I put this to ground. Okay, let me okay, now pin 4, so if this is pin 6, pin 5, pin 4, so here we go. Okay, we get a very, very low ohms. I get a bit less than half an ohm. Now, is that good or is that bad? It's actually, you know, okay, but okay, all the other tubes are still in circuit. So, and since all the tubes are mounted in parallel, I could be measuring the filaments of all the tubes in parallel. So, well, I would say, okay, maybe the secondary filament is good, maybe. So that's okay. Now I'll measure that in another way. Yeah, I'll hook up the whole sweep generator to AC power, and we'll see whether the filament secondary works that way. Now there's one last winding on the transformer, and that one is a bit of a problem, I think. So you see, this is a filament winding which measures pretty much like a short, but I think that's because I'm measuring all the filaments of all the tubes down the line in parallel with this winding, so I would get very low ohms anyhow. But we also want to measure this part here. Okay. Now, as you can tell, the dial light, or I should say the pilot light, which is on the front of the cabinet, is also hooked up to that 5 volts right here. Yeah, so if you follow the 5 volts line, you see it goes to the pilot light as well. So if we measure at the pilot light, I should be getting some sort of reading, provided that let me see. So provided that this line here, which goes through this resistor and then through a potentiometer and then another resistor and then into the coil, well, provided these don't interact too much with the 5 volt secondary of the transformer. In any case, let me see, this is 1.5 plus 7.5 is 10, plus another 10 for this variable resistor, which is 20, and say for give or take this would be 100 ohms, let's say. Okay, so let's say this is 100 ohms right here. Yeah, so I should be measuring something around the 100 ohms mark if I measure at the pilot light. Okay, and where is the pilot light? Well, it is right here. I'll show you. The pilot light is that thing right here. Okay, so I got the multimeter hooked up to ground. Let me adjust my camera a bit. Right. So, let's measure right here. I was afraid of that. It gives practically a short. Okay, so, well, the problem is really pretty much the same I had with the filament winding on the transformer, which is that since I have a pilot light and the coil of the sweeper capacitor in parallel, I'm not getting a very useful reading. In any case, the circuit isn't open, so I have good hopes that the secondary, both the low voltage secondary coils of the power transformer are good. I forgot to tell you about another interesting detail, which is this shaft here. This shaft is of the IF signal alignment, let's say, and you see it's also wood. Well, I don't know if you can see it, but I can see all the little grain on the wood and all that. So they actually used a wooden shaft on this variable capacitor for the IF tuning, let's say, on the sweep generator, which is kind of interesting as well. The same as what they did on the rotary switch shaft, which selects all the sweep frequencies. They used wood instead of plastic or bakelite. Pretty much for the same reason, I guess. On the one hand, because wood does not conduct RF signals, and on the other hand, because it's cheap. Probably cheaper than plastic or bakelite. Well, at least in that period. Okay, so, well, let's say I'm reasonably confident all the capacitors except one I still need to replace. This one over here. Yeah, but except for this one and the odd mica capacitor like that one, all the other caps were replaced, and I also replaced all the out-of-spec resistors, which were, I don't know, say 6 or 7 of them. So I replaced all those as well. So I'm pretty confident that when I get the good replacement tube for the 686, which was broken, we can power this sweep generator up. Now, will it work correctly? Well, I guess I would have to say no, since I changed a lot of parts, even in the high frequency section, so right here, which is all high frequency. It's quite possible that the whole sweep generator will be completely out of alignment, which means some extra fun aligning the sweep generator. I've never tried it, but the instructions in the service manual seem reasonably complete, so I think I will have a stab at it and well, try to align it. Right, so one last thing before I finish this part of the video. You see that I replaced quite a bit of the connectors by BNC connectors. You can see them sticking out there. Yeah, so, and I did that on 3 spots to be exact. So the scope connector was replaced from an RCA jack to BNC. The IF output connector I replaced, which was also a crummy RCA connector, I replaced by BNC, and then this. Now, remember I told you that RCA proposed in its service manual to have an upgrade installed in one of these sweep generators. Well, I think this connector, which was an RCA and which I replaced by a BNC, is exactly that, is exactly part of that upgrade RCA proposed. And so, therefore, it's quite possible that all the extra little things we see in here, you know, the changed capacitors, different wiring and all that, well, at least in certain parts, were all made at the factory by an RCA tech to build in that upgrade. So yeah, this is supposed to lead out a unattenuated swept signal, whereas this one is an attenuated swept signal. And they say that they lead out an unattenuated one as a reference signal. Okay, interesting. So, well, once we start this sweep generator up, we'll hook this up to the oscilloscope and then we'll have a look. Okay, I bit the bullet and I unmounted this stiff assembly, which was originally attached to this variable capacitor assembly, and I'm going to replace it by a construction of my own, which would be a small PCB with some components built underneath the chassis, so underneath this hole, and with a coax wire running into the variable capacitor, running through the hole and then underneath the chassis into that impedance adapter I'm going to build. And then I'm going to cut a small aluminum panel which will fit exactly behind this hole where the original RF output connector was mounted. And in the aluminum, in the tiny little aluminum panel I will build, I will mount a classical BNC connector. So that's the plan. Now what am I going to build? Oh yeah, one more remark. You see the back panel here, and I tried to clean it with ammonia, which I always do with stuff which is full of grease and smoky residue and nicotine and all that, and it turned black. Now my days of chemistry are long behind me, but I think this means that for whatever reason they silvered the sides of this box. You know, they silver plated it. Now why? I really have no clue. Why would you silver plate a simple metal box? Now the reason why I'm saying it's probably silver plated is that silver and ammonia produce a brownish or blackish residue, which looks like this. Yeah, this looks like oxidized silver, whereas aluminum reacts in a totally different way. Aluminum becomes whitish when coming in contact with ammonia. So this is really peculiar. Anyway, I will have to find a way to clean it off a bit, although nobody will ever really see it. Still, it bothers me a bit. So I know nitric acid would do the trick, but I'm not really fond of using a quite corrosive acid on this. Yes, I tried navel jelly, and it didn't really help, although I have to admit I used diluted navel jelly. So I might give a try with undiluted navel jelly, but I doubt phosphoric acid will do anything to solve that little problem. Anyway, that's a problem for later. So now let me show you what I'm going to build. That's the circuitry I'm going to build. Now it's not a very complex piece of circuitry, but it will perfectly do what I want it to do, namely to adapt the output impedance of the RF output and combining the two channels that come from the sweep oscillator into one. I might tinker a bit with the values once it's built and installed, but I think it will do perfectly for what I want it to achieve, namely to combine two RF output channels from the attenuator capacitors into one RF channel, or one output RF channel. It will be a tiny little PCB, and which will fit nicely inside the chassis. So let's get building. I prepared all the parts necessary to build in, together with a small BNC connector. So what I'm going to do next is mount the coax cables to these contacts you see here, okay? And when that is done, I'll connect them up to the small impedance adapter and the adapter to the BNC connector. But before I get there, I still need to make a small mounting plate to mount the BNC connector into that hole. Right, I mounted the whole setup inside the sweep generator. As you can tell, I made also a little sleeve out of copper foil, which I bought quite a while ago, well, just to keep them together. But on top I did the same thing, but that's more important actually, because as you can tell, the little copper sleeve is what holds together, what clamps the wire, in fact, to the variable capacitor. And as you can tell, I made my own little copper foil sleeve, and there are the inner wires of the coax cable. So I passed the coax through the original hole in the chassis, which is over there, okay, and I left enough slack so that when the assembly moves back and forth, the wire won't pull on the BNC connector, which I will ultimately build in to that hole over there. So that's where I'm at. The next thing to do is to build a small aluminum panel which fills the hole here, and which has a hole in it into which I can build a BNC connector.